This is the voiceover narration for my videos on the rotation experiments. This cone-shaped cup is rotating at the same rotational velocity, but of course the outer larger circumference needs a larger tangential speed, and the same thing is happening here, where these two cups fasten at the large ends. Once it tries to veer off, it will actually come back on because the tangential speed is larger for the larger circumference end. Here they are glued on the opposite way, and it rolled off because the tangential speed for the larger end was larger. On a cylinder, it's semi-stable. The tangential velocity is the same no matter what, and of course here it was at an angle.
The moment of inertia, also called rotational inertia, depends on the mass of the rotating object and on its radial distribution. Therefore, a hoop has a larger rotational inertia than a solid disk and is therefore harder to accelerate. Due to its larger rotational inertia, the hoop also takes on more rotational energy. Therefore, less translational kinetic energy is available from the original potential energy on the top of the incline. Therefore, it is slower. Understanding what the movement of inertia means is of course important for any kind of rotating machine parts.
The stick with the weight on top has a larger rotational inertia than the stick with no weight. Since torque is force times lever arm, and torque is also moment of inertia times angular acceleration, the angular acceleration for the weighted stick is much less. Also, since the bare stick's center of mass is already closer to the ground, it needs less time to rotate down. The frozen juice has a large moment of inertia and therefore the weighted stick and the hammer have a larger rotational inertia when the weight is on the top compared to the weight being on the bottom. Since torque is force times lever arm and torque is also moment of inertia times angular acceleration, that angular acceleration is computed to be much smaller when the weight is on top, and therefore one has more time to balance the stick or the hammer. Ben is placing a weight onto the meter stick. The pivot point is his thumb and his index finger, and the back of his hand, in this case the other muscles from the other three fingers, are the torque that is counteracting the weight's torque. And the further he plays it from his hand, of course, the harder it gets for him to hold it, because he only has that short lever arm, which is his hand. So with the larger torque from the weight, its larger lever arm, and his fixed short lever arm in his hand, he needs a large force in his hand muscles and arm muscles, of course. For the broom to balance at its center of mass, the torques on the left and on the right must balance each other. Thus, each must yield the same torque, which each is mass times gravity times the essential lever arm. Once the broom is sawed into two pieces, it becomes evident that the stick has a longer lever arm than the brush part. Hence, the stick's mass is less.
In order to turn the nut on a bolt, a torque, which is force times lever arm, must be applied. A longer lever arm permits a smaller force to overcome friction between the nut and the bolt.
The food tray is basically the same that Benjamin did earlier with the stick and the weight. So here I'm putting my hand at the center of mass of the tray, and now I'm going to put it at the end with actually the heavy dishes close to me. So I have to exert a relatively small torque. Now I turn around so that the heavy dishes, the mayonnaise jar, by the way, is empty. So now the heavier dishes are further away, so longer lever arm means that I have to have a larger torque. For the triple beam balance to show a correct reading, the torques on the left and on the right must balance each other. Thus, each must have a torque that equals mass times gravity times lever arm. The counteracting weights supplied with the balance do of course not change their masses, but placing them at different distances, that is, changing their lever arms, produces the necessary torque. There are extra weights supplied so that the balance is able to register beyond 610 grams. These weights have a mass of just 285 grams, but due to the torque that they produce at the end of the lever arm, they are equivalent to 500 grams.
Throwing and thus accelerating the dumbbell requires a force by the hand, which of course produces an equal and opposite force on the hand. That force, acting on the outstretched arm, produces a torque which accelerates the turntable and sets it in rotation. While the torque exerted on the body is easily pictured, the torque on the dumbbell is interpreted as its force times the same lever arm to the rotational axis of the turntable. For the board to balance, the torques on the left and on the right must balance each other. Thus, each must have a torque that equals the mass times gravity times lever arm. The lever arm to weights is obvious. The board's lever arm is measured from the pivot to its center of mass. The measured masses match the computed masses.
The apparatus consists of V-shaped rails that are inclined. If a cylinder was placed on them, it would roll down, pulled down by gravity, of course, this incline. The double cone is rolling down as well, pulled down by gravity. But due to the rail's V-shape in the opposite direction, as the rails spread out, the double cone center of mass is lowered. It is still rolling down. As long as a person's center of gravity is above their feet, they won't topple. But once that center of gravity is off, gravity produces a torque which makes the person fall forward and down. The closer a finger is to the stick's center of gravity, the more weight it supports. The more weight a finger needs to support, the more friction is present. Thus, it is easier for the other finger to overcome the lower friction on its side. Therefore, both fingers are inching closer to the stick's center of gravity. The water in the swirling cup is changing directions, always being pushed towards the center of the swing. Thus a centripetal force must be present, provided by the support force of the cup's bottom. Without a bottom, the water would spray tangential due to its inertia. For each object to be able to turn, it needs to change its direction, and for that a centripetal acceleration and thus a centripetal force is necessary towards the center of the turn. For the banking airplane, the partially sideways lift exerted on its tilted wings supplies the centripetal force. For the turning car, it is static friction acting perpendicular to its turned tires, and for the moon, it is Earth's gravitational force. The forces exerted on the car are its own weight, the track support force, which is perpendicular to the surface, usually upward, slightly sidewards too in a bank curve, as well as sideways from its rails. Static and kinetic friction, air resistance, and finally the roller's friction that launch and accelerate the car. In the loop-the-loop, it is gravitation and the track support that supply the centripetal force to keep the car in the loop. Since there are no outside forces, angular momentum must be conserved. When the massive dumbbells are pulled inward, the moment of inertia is reduced. Thus, the angular velocity is increased, so that angular momentum remains the same. One could argue that there should be a torque inside the system because the turntable and person accelerate. While the dumbbells are pulled towards the turntable center, the movement is not radially due to the rotation. Thus, there is an angle between lever arm and force, and that produces a torque that accelerates the turntable. Since there are no outside forces, angular momentum must be conserved. The clockwise turning wheel's angular momentum is clockwise and must remain so. When turning the massive wheel over, its angular momentum is now counterclockwise. Thus, the turntable and person must have a larger clockwise angular momentum so that the original angular momentum is conserved. Of course, there also needs to be a torque to turn the wheel, and it is equal and opposite torque that accelerate the turntable and person. Finally, the person notices that it is much harder to rotate a spinning wheel than a non-spinning one. Due to its larger angular momentum when it is spinning, it resists the applied torque and thereby also produces a precessional torque that tries to tilt it away.
Quote from Wikipedia. To play with the kendama, one holds the toy and pulls the ball upward, so that it may either be caught in one of the cups or land with the hole on the spike. For the novice, like myself, this works best. By spinning the ball, it starts with some angular momentum. Any torque exerted on the ball, especially by me jerking on the string, has a harder time to change its angular momentum, and thus its orientation of spin. Therefore, it lands more easily on the spike, with the hole pointing downward.
While the experiments look quite simple, the explanation behind them is really rather difficult, so therefore I posted some websites to access to figure out what precession actually means and why these gyroscopes are precessing.